y'all hear me? So I'm Bex. I decided to come here to ramble a little bit. I work at Knoxville Industries. Previously, I studied security at Gratis at Dartmouth Trust Lab. And yeah, I'll just continue on. So in my research, I wanted to find the root of trust. So I looked to many places and didn't really find that much besides, well, I guess a TPM that is kind of what people are considering the root of trust, but it seems a little elusive to me. So I wanted to kind of go back and just think about trustworthy software. And there's like the classical view of confidentiality, availability, and integrity, but I don't really think that's enough to really show what we want from trustworthy software. What we want is software that behaves as expected, doesn't have any unexpected behaviors, is predictable and reliable. And to really get at that and to be able to really create trustworthy software, especially out of the complexity that we're seeing these days, we need to think about the policies we apply to it, what we expect our software to do, and what we allow it to do. And I think a lot about, is there an ideal size, granularity for policy objects? And so through this talk, I will be talking a little bit about type theory. I'll talk about loaders, a bootloader, U-boot, and the runtime loader for ELF. Then I will kind of go into my memory regions as types are policy, and think a little more about this one-size-fits-all, like how we can get away from that and start having policy objects that really better encode our intentions in what the software should be doing. This doesn't look so nice, but finding the right granularity. So when I talk about type systems, I kind of generalize a little more. Most folks' usage of types is programming language centric, and it really applies to programming language constructs, data and function calls. Function parameters, parameters of a function are assigned to type as return values, and it's up to the compiler or the runtime to really ensure that data of the correct type are being passed to that function and being returned from that function. And these type rules will enforce these relationships between the different constructs. But there's so many other things that kind of seem like types to me. Really, because types generally define what operations are allowed on objects, what behaviors are allowed. And there's a lot of constructs that exist outside of programming languages that really have this field to them. For example, when we're loading data into a memory space to set up a process, really the regions that we're copying over are objects. They have, each of them kind of has a purpose to this group, to this region there. And just to give you a little more sense of where types are used, so interpreted languages, there's types. Sometimes these are often dynamically, what's the word? Tested. So if I try to, say, add an integer to a string in Python, it complains and there's a type error. In Ruby, there's a similar thing. If I try to do the same, JavaScript, special. And it has a lot of weirdness, and I couldn't really find good examples, and there's a great talk of WTF.js on YouTube that has a lot of interesting weirdness of JavaScript. So I find if you do type of a string, it'll tell you a string, but if you ask it if a string is an instance of string, it will say false. So types aren't, types have this purpose of helping really bring the attention explicitly to our code, but I mean, there's some languages that don't do it as well as others. And then of course we see it a lot in compiled languages, and what would happen is if you don't adhere to the type constraints, you'll see compiler warnings or errors. In C, it's mostly warnings like, well, you didn't cast this as an integer, but we could treat it as one if you do. And so Java's a little more just, you might lose some lossy conversion from double to int. And Rust has a lot of really interesting uses of types to ensure concurrency and memory safety beyond what we see in just Java types, C types, and so forth. And Rust has really been a language that they've been pushing to do systems programming, low-level stuff, and as an alternative to C. But it hasn't really been picked up by the general public so far. It's used a lot in Firefox because it's a Mozilla heavily created language. Then there's other types of types. And also when I'm thinking of types, I'm thinking of compiler injected policies. So stack canaries are kind of this type enforcement on the stack. So if some important function pointer gets overridden, there's a type error at runtime that's like buffer overflow. Dependent types are kind of interesting. The example I wrote, it doesn't actually compile of anything, but dependent types, the idea is your statically checked types are actually dependent on runtime values. So you might not actually know at build time that it type checks properly, but one thing you can do with dependent types is you can say have a list of length 2 and have that be a type. And if you try to create a list that has more or less than 2 elements, it just won't compile. And there's a lot of this has not been used too much, and you can't really generally type check something statically with this method, but there's a lot of interesting work there. And type state is something that I thought was very related to some work I did and what stuff I'm going to be talking about here. The idea is you have an object of a type, but sort of the functions you can call on that object are dependent on the state it's currently in. So you can maybe you're allocating something and deallocating it. And after you allocate it, you can read and write or deallocate. But if it's not ready in that state, the only thing you can do is allocate. And so that is definitely a nice intention-based policy right there. It's not always checkable at compile time, but there's of course it was sort of an older idea in programming languages, in that sort of research. It kind of lost popularity, but yeah, it's something that's very interesting to me. Control flow integrity, which we see used these days. And so I kind of think it as a compiler injected policy. So there are kind of branches along your control flow graph that you think that are valid, that you're allowed. And the idea of control flow integrity is that you disallow jumps across branches or things that are not explicitly allowed in this policy. And so if it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. So when it comes to type policies, they definitely are useful in helping you write code, or especially the types that we use, most types we use, they help you write code that kind of keep with your intention of what this function is supposed to do. But it's very much on this functional module level, and it doesn't necessarily easily expand to entire program behaviors and ones that we're interested in. And that's what I want to try to get at with some of the work that I'm going to present. Types outside of programming languages, ones that aren't, these things I consider types in their own ways. Like file permissions can be felt like a type, and there's some enforcement there by the kernel. SE Linux sort of is this very fine-grained type system on syscalls over in Linux. And then there's this coarser one, read, write, execute permissions across pages. So moving now from this type talk to a policy, how is policy like training a puppy? Well, it helps that your policy objects are well sized. So if you're Alice and you shrunk down and you have this ginormous dog, it's not going to want to play with your tail stick. Interprocess. I kind of thinking a lot of work has been done on interprocess and intra-process. So interprocess, we have Unix file permissions that are fairly coarse, and their protections are against labels on the file, depending, and then versus the process, a label on the process is running, who owns that, and that's pretty coarse. And SE Linux is kind of pretty hard to work on. It's a bag of permissions that you really have to strictly define across files, type versions of syscalls, types of syscalls, and domain, which is, you know, sort of like the runtime label again. Intra-processed, we will see read, write, execute permissions on pages, and that can be too coarse. So we see if there is a function pointer in writable area, you don't always want to be able to overwrite that. And there's, you know, the C type system, which kind of seems weak. You can always cast something in like the compiler, well, you can compile it anyway. Compiler will pretty much let you do everything unless you like tell it to, you know, make all warnings errors and also, you know, screen with all the warnings. And I'm wondering now with region-based types, when you think about regions of memory, there is no actual like specific size. It's very variable. You can have a very large region of memory, or you can think of a single object. And maybe that's a just right. And when we want this right granularity, whatever it is, it should really help us more easily describe what matters to us in software behavior. So when we're crafting a policy, like what is this wish list that we want? And I love this term that Sergey used in a Black Hat talk earlier, the policy wish list. We need to be able to really say in our policy, be it types or types with other things, we want to say what's relevant, like what data is very sensitive, and describe what matters. And perhaps certain operations have to happen in a certain order. It can be harder to describe that with the type systems and these fine-grained ones and these coarse-grained ones that we have, you know, in practice. Another policy idea for policies, or another thing we might want, is to be able to be concise and describe only what matters. Because time, well, it's not well, we die eventually, I'm sorry to say, but you can't take forever to write a policy or for your software because it needs to, you know, be used, I guess. There's probably a reason why you're writing it. So we sometimes just need to focus on what matters. And I'm picking on SE Linux again, but it requires you to assign types to everything and to assign permissions to every single syscall that might be performed on any object that is part of its language. Which is usually files. So what does matter? To me, it really depends on the software and the larger context in which it's being run, in which it's being used. And I'd like to explore that a little as I continue. So what do we want? Intense level semantics. Again, this is borrowed from Sergey, the Goshtektistinsky doshes. So we don't really know what those words are. We know the, but there is a grammar between them that reveals relationships. So even though we might not know exactly the layout of code, module, functions, etc., what every single one does, it's easier to understand the relationships between them. And semantics can be derived from relationships. And intent can be derived from these relationships. And we can start using that to create policy. And not only that, but code, you know, it executes, it has different phases. So perhaps an object at a certain time in execution is not sensitive, but eventually it will become sensitive, or maybe it needs to be used. So in some hypothetical email client, it may initialize itself, authenticate with some key, and then after this authentication process, you know, to some remote server, it will start processing input, handling errors, doing a session, and it'll eventually de-authenticate. Why should it be able to why should the code that processes input ever look at keys again? It's already been authenticated. There's probably a small session key just for that, but it's treated the same currently as every other object in memory as the email client executes. And with these different phases, we should really be able to say this region, these types of objects here are important and readable and writable. But while we're executing this other phase where we're handling untrusted input, let's lock down the sensitive objects. so that we don't, so that some runaway process, because there's always going to be like some issues with the parser, right? So something that happens doesn't necessarily leak the keys. So we don't want the keys to be leaked to the interwebs, but because everything sits in a single address space, it can happen. I mean, this is in our hypothetical email client, but this is something that does happen. And so why do we allow this? U-boot is a bootloader that's used in embedded devices. And this is something that I dug into deeply when I was thinking about regions as types. So before I go, a bootloader, which I consider as a type of loader, to me they're sort of the same thing. So the loaders are the magic that transform a binary image into a running application. And it sort of does this transduction based on metadata in the image and what it knows about the runtime. In the binary image, what I mean by binary image is a static representation of the machine code. So ELF is the type used in like Unix, Linux, X, PEs, Windows, Mako or Macho, however you want to pronounce it, is the one in OS X. And then also two more things. Address space is the term I use to refer to any addressable memory as the code is running, anything that's reachable, so it's the entire address space. In memory map, I think as a model of the address space where there's semantic labels on the different regions, and this naturally happens whenever software is executing, because there will be a chunk that's it's code, a chunk that's data, and a chunk that's a stack, so forth. This is just natural. Who loads the loader? Well, it's another loader. It's loaders all the way down. And the bootloader is just a term that I use to mean like the loader that executes before the kernel or the primary application is. And so we've seen plenty of them. So what do we expect from our loaders, and what's unexpected? Well, I expect that really any loader or bootloader will do discovery and initialization of the resources in the address space or the hardware that's part of the larger system, especially if it's a bootloader. It will prepare the address space for whatever needs to be run next. It might actually have to relocate itself to another place in memory, especially with bootloaders that are in confined regions of, if there's confined resources early on, a bootloader might need to move itself out of the way. It might actually enable some more RAM, copy itself over there, and then continue on. And also, you expect the bootloader to prepare this image in memory and finally execute it. So I like to think of, that in stages. The loading seems to be a very, forward-going process. You'll start and you'll do some bookkeeping, and perhaps at some point the stack will be available and be available for the rest of the time. And then you enter another phase where you're locating the target image. And that's more bookkeeping. And after you do that, you'll see that there's more data. There might be a heap available. There might be a VSS region that's zeroed out and ready. And then there might be another phase of loading the target image and doing preparations. Eventually, the target will be ready, and there's like this final phase that we can execute that and jump into the target. Now, metadata, Weird Machine, is some of the work that originally inspired me to think about regions as types. So how a loader is expected to work is that it will read metadata in this file that it's parsing out. Well, first it might actually copy everything into memory, and then it'll start reading out the metadata to figure out what it's supposed to do. And it will start patching regions of addresses in memory as needed, because it might need some absolute addresses that are not known until runtime. And then it continues and it looks to see with its own data structures whether there's more that it needs to patch, another library that's loaded. But this doesn't have to work this way. And some broken promises results in a Turing-complete loader, which I presented before at DEF CON and TCC. If you're interested in that, I can give links later. But in this execution model, or if you have weird metadata, you might see the loader reading it, writing all over the address space because of the metadata is just telling it to do so. And then it will end up reading again and finding itself patching again into the metadata and actually running them as instructions. And suddenly you get this, you can do arbitrary computation with these metadata, but really the only thing they should have been doing is writing to very specific regions of memory. So in my mind, this is a type confusion issue. These metadata are meant to, and the phase in which they're processed is really only meant to write to certain regions of memory which contain places that should have, say, absolute pointers. But in this weird machine, it's writing to regions of memory that should never be written to while the loader, after the loader, reads in the metadata. It's overwriting its own metadata in order to get the loader to do, well, Turing complete computation. And so that seems like type confusion to me. So going to U-boot, I didn't do anything as interesting with U-boot, but there is a lot of trust in some instances or some builds of U-boot. How should it behave? I specifically looked at the U-boot SPL for the BeagleBoard XM. The BeagleBoard XM has multiple rounds or stages of bootloading. One is sort of this on-chip ROM, then it invokes an SPL, which is a smaller, in terms of code size, bootloader, which then invokes a larger chunk of U-boots, an entirely separate image, and then finally Linux. So I was just looking at the more simple one, which is really a subset of the larger main U-boot image. While looking at this, I was wondering, does this bootloader always behave, yes, does it always behave as it's expected, never behave unexpectedly, act predictably, act reliably? And how does U-boot accomplish what is expected of it within the context of behaving as expected and never behaving unexpectedly? U-boot, one of its expectations is to discover resources. And, oh, you can actually kind of read this, cool. Just to give you a sense of what it's doing when it's discovering resources is that there's sort of hard-coded discovery where addresses of memory mapped hardware, memory mapped I/O, is just known, compiled in statically into the binary, and it will read a value to get, say, the sysboot status, which is, why is this bootloader invoked? Is it a cold boot, a warm boot, etc. Then there's sort of semi-hard-coded, where U-boot, as it's running, will know some values of a register, perhaps, and use that to look up in a table to figure out how to use this hardware. And then it will also need some protocol-based discovery. It will know how to send and receive, or really work with MMC, that protocol, in order to read the SD card. And it has to, in this case, it knows how to read a fat file system in order to find this next stage. So these are the different discovery modes. And how it uses resources is often based on what it discovers, sometimes based on hardcore addresses. So this is an example of it setting up or writing to the I2C bus. And the bottom table is just the documentation on the chip of the address of each of these memory mapped registers, and they correspond to these magic numbers in the code itself in order to make use of these resources. And again, when it's loading images, it's crawling the file system, parsing headers, and using that header information to figure out what to do next. And don't read this, it's just, it also sometimes relocates, and the relocation is also based on hard-coded information as well as, well, mostly hard-coded information. It knows the size it is, so it can move itself elsewhere, and it doesn't necessarily know how much room is available. It just assumes it won't overlap with anything in this particular case. And so these are things you might see. And along these things it does, you'll see these relationships between resources, memory regions, and then also the phase in which it's executing will use different resources. So in other words, it will focus on read and write to different memory regions. And this is an overall address space for this particular chip in the Beagle board. This is from the documentation. And there's a region that there's a lot of reserved space, but there's some addresses, physical addresses that are like the on-chip boot from. There are some physical addresses that are the on-chip RAM, then a lot of regions that are for different hardware resources, for different memory mapped registers. And if we zoom in to one of these areas of memory mapped registers, we'll start seeing, the I2C, something for R2C, something for some timer registers. And so really, these regions of memory are objects, and these objects can really be part of a policy. And we can decide, because region sizes can be as big or small as we want, we can have a course policy that's like, this region, these are all registers, and at this point we should not be touching those. Or you can have a policy that's like, this region of memory is the MMC registers, and we're going to only be using those, and we don't want, for some reason, to overwrite some other types of registers because, how it's interacting with the MMC. And with embedded stuff, there's a lot of silent failure. So you might not even see in your testing of it that you're writing to weird spots. I wrote a policy and tracked all the reads and writes for U-boots. And I actually had a script that went through all the tables in the documentation of registers, found their addresses, and looked to see if any addresses that were not, any read-only registers in the table were written to ever. And I also wanted to see if there was any addresses that were not specifically defined as a valid address in this, in the documentation, to see if any of that was written. And I actually